Well, hello, people. Today, go away back to tab. Okay, today I have something to show you. Here I have a little device. It kind of looks like a hot glue gun sort of situation. And what I'm going to do is I am going to connect it here. Ignore like the batteries all over my desk. I'm going to connect it here to this little light bulb. And, sorry, this is off screen, but it's all happening. The magic is happening. What I'm going to do is I'm going to connect it to this little light bulb here, and we're going to see if I can tip this down so that you can see it. Oh, look, this is my little writing pad device. Isn't that so cool? Yes, so cool, Miss Wilson. I know. Okay, now here is my little light bulb, and here is my little hot glue gun looking thing. And let's move my light bulb right here. Let's turn off the lights so that you can get a really good view. Okay. And now here's what we're going to do is I am going to crank this little hand crank right here, and here's what you're going to see is the little light bulb lights up. And you can see that the slower I crank the hand crank, the dimmer it is. And if I crank it really fast and it gets nice and crazy bright. I actually really don't know like how the little like camera situation is picking up on this situation. And like how well you can tell like relative brightness is. But the main idea is that the faster I spin this thing, the brighter it gets. So that is a pretty fun toy situation going on there. Now enough with this light bulb. Let's try something else. Okay, suppose that instead of connecting it to the light bulb, suppose I took this little battery here, and once again, I'll tip it down so that you can see it. Suppose I took this little battery here, and I am going to take this little cap off this battery, like this. And now, what I'm going to do is I'm going to hold this, okay. I'm going to hold this here, and I'm going to attach this end to the negative terminal. Actually, I'm going to do red to positive, because that always feels nice. And I'm going to attach this black end to the negative terminal, and I want you to watch what happens. Wasn't that fun? And now check this out. You can see it rotates this way. Check out what happens if I flip these. So I go positive here and negative here. You can see it rotates the other way. Once again, give it a nice flip. Whoops. Positive here, negative here. And then again, flip it back. Isn't that nice? Now, this device is what we call a handheld generator. And we're going to see exactly how this little guy works to light up a light bulb, and exactly how this little guy tends to spin when connected to a battery. Today, we're talking generators, we're talking motors, and lastly, we're talking transformers. Those are our 3 topics of the day. Let me go ahead and get situated here. And we'll take this little guy. We'll not pull the cord out. That is goofy. Don't worry, guys. It's just unplugging. It can get plugged back in. We'll wrap the cord around it like this for proper and safe storage. Then we'll set it off to the side here. Put a little cap back on my battery. And guys, we are good to go and good to learn, except that I put my tablet on the floor. Okay. Here we go, team. Let's talk generators, motors, and transformers. The first thing that you need to know is what a generator is. We'll start by talking generators today, then we'll talk motors, then we'll talk transformers. Here's a nice definition for you. A generator is a device that converts kinetic energy, let me try again. A generator is a device that converts mechanical energy into electrical energy. A generator, once again, so that you can write it down here, do write it down in your notes. A generator is a device that converts mechanical energy into electrical energy. If you have something like this, what you do is you spin the handle. You take motion energy and you turn it into electricity. You use it to light up a light bulb. That's what a generator is. A generator takes mechanical energy and turns it into electrical energy. Now, if you're thinking about how you could generate electricity using mechanical energy, if I were you, I'd be thinking Faraday's law. Here's what I'm thinking. Faraday's law says that if you want a current in a wire, if you want to create electricity, all you have to do is change the flux in a loop. So I'm thinking if I want to create electricity, then I just got to get a loop and change the flux through it. And that's exactly what a generator does. I'm going to show you a picture of, actually I'm going to show you 3 pictures of what a generator looks like. 1 second here, let me get it pulled up. Doop. Look, it came pre-drawn. Is that not super awesome? So cool and high-tech, Miss Wilson. Here they are. Here's a generator. For now, I just want you to focus on this first picture, and then we'll walk through the second picture and the third picture. Here's what's happening in this first picture. If you could look inside my little generator here, I'll blow this up a little bit. Okay, if you could look inside this little generator, do you see that there are like these little wheels? Well, that part is just connected to the hand crank, so that's just making stuff spin. Then you have in here, do you see this little silver cylinder here? If you could look inside of that silver cylinder, what you would see is you would see a loop of wire between 2 ends of a magnet, a north pole and a south pole. Now notice here in this diagram, I haven't drawn the whole magnet because that takes up a lot of space. So I only drew the north end of one magnet and the south end of another magnet. But that's what you would see inside this generator. You would see a little loop of wire in a magnetic field. Here's the idea. If we can change the flux through the loop, then we can create electricity. Now, you already know that there are 3 ways to change the flux. You could either change the strength of the magnetic field, you could change the area of the wire, or you could change the orientation of the loop with respect to the magnetic field. Well, to do this one, we have found that it is easiest to change the orientation of the loop. What you do when you spin this little hand crank here on our little generator is you are spinning this little loop of wire that lives inside of a magnetic field. And if you're spinning the loop of wire in a magnetic field, you're changing the flux through that wire. And if you're changing the flux through that wire, you are generating electricity. Here I have 3 pictures because I'm showing the spinning of the wire. What you'll see, I'm going to shrink this down a little bit. What you'll see here in my first picture is that actually, I kind of need my loop. I left my loop in the other part of my classroom. Hang on, let me go get it. I'm going to pause really quick and grab it. Okay, I got it. My loop of wire. At this point, you're probably sick of seeing my loop of wire. This is my favorite loop of wire. It is just so wonderful and so perfect for physics demonstrations. Here you'll see that I attached a little piece of pink sticky note onto one side so you can see where that one pink sticky note is. Here's what I want you to see here. I'm going to flip this way. Here's what I want you to see is that this is a picture of a wire rotating in a loop. So what I wanted to show you is I wanted to show you that a wire starts in a loop like this, and then it's going to turn this way and end up this way in the magnetic field. Now what I showed here is I showed this long edge of the wire here. I made 2 different lengths of wires. This is a long edge and this is a short edge. That's so that you can see it turning. So here's the long edge. Then this long edge is going to swivel out to face you, and then it's going to swivel and land over on the other side here. So it's pivoting around the shorter side is kind of a way to think about it. Then I also put a little pink little sticky tab on this side. This side is like the long edge of the wire. You'll see that the long edge of the wire starts out on the left side here. And then it's going to swivel out towards you and pivot around and land on the right side like this. So that's kind of what I want you to see when you're looking at this wire here is we're looking at a rotation of the wire in the loop. Or sorry, a rotation of the wire in the magnetic field, and I want you to be able to like kind of visualize that. So that's what we're looking at. And with the 3 pictures, we are looking at 3 parts of the rotation. We have the first part of the rotation here, the second part of the rotation here, and the third part of the rotation here. Now, we know that changing the orientation of the wire is going to create a current in the loop. Let's look at exactly how that's going to happen. And I'm going to change my color here. Let's change it to blue. Yay, blue. Okay, let's get rid of that. Bye. Please leave. Bye. Okay, here's the idea. What I want you to see right now is I want you to see that as this little loop rotates, this side of the wire right here is going to be coming out of the page towards you. And this little side of the wire here is going to be going into the page away from you. So what's going to happen here is that we have a magnetic field, and now we have a little wire that is moving in that magnetic field. And that wire is made of charges. If this wire is moving in the magnetic field, then we just created charges that are moving in the magnetic field. So now we have charges moving in a magnetic field. You know that if charges are moving in a magnetic field, the magnetic field will create a force on those charges. So here's the idea. Use your right hand rule. My fingers point in the direction, oh gosh, this is the whole thing where I can't like do this the right way. Okay, but you know what to do here. My fingers will point in the direction of the magnetic field from north to south. Then my thumb will point in the direction of the movement of the charges. The charges are coming towards me, so I point my own fingers from left to right. Then I point my thumb pointed towards me to show the direction of the motion, and my palm is facing up. That means that the charges, the positive charges, are going to get shoved up along this wire. So all the positive charges are going to get shoved up. Meanwhile, along this wire here, my negative charges are going to get shoved down because that's the way that the back of my palm is facing. So the wire, the magnetic field, as this wire moves, is going to shove positive charges up and negative charges down on the left-hand side. Let's look at the wire over here on the right-hand side. The wire over here on the right-hand side is going into the screen. So what I'm going to do is I'm going to use my right-hand rule. I point my fingers in the direction of the magnetic field. My thumb goes in the direction that the wire is moving. And now I see my palm, if my fingers are pointing to my right, my thumb is pointing into the board, then my palm is facing down. So this is going to cause the little positive charges here to run down. Meanwhile, the little negative charges will run up. Here's what this is going to cause. Do you see how we're going to get positive charges that are moving in a loop? So the positive charges are all going to run around up this side of the wire, across this part of the wire, down this side of the wire, and all the little positive charges you can imagine. This isn't really like a right way of talking, but you can imagine as if all the little positive charges are all going to pool up right here. So you're going to get tons of positive charge that lands right here. Meanwhile, all the negative charges are flowing back the other direction. So all of the negative charge will land right here. And this end, you can imagine, will become like a puddle of negative charge. Now, really, we all know that this is wrong for several reasons. First, because the negative charges or the positive charges don't actually move. What actually moves in a wire is negative charges. So the negative charges you can think of as the negative charges are going to flow this way, and they're going to leave behind a little puddle of positive charge. But to say that they're all going to pool isn't totally correct either. But that is a way that you can think about it. You can think about it as all the negatives pulling up over here and all the positives pulling up over here. Now, if I connect this generator to something else, let's say that I were then to connect this generator here to a light bulb, like this. Let's say that we were to connect it here and here to a little light bulb. Well then, wait, I'm going to redraw that. Sorry, I don't love it. I just don't love it. Okay, try again. Oh, okay, well, yeah, sure, extremely try again. I didn't really mean it that extreme, but that's what happened. Let's say that I were to connect it to a little light bulb here. That little light bulb would then experience a flow of current. That current would go from the high potential place to the low potential place. And current would flow this way through the little light bulb, and the little light bulb would then light up. And isn't that what we saw when we used our little generator? Is that as I turned the little wire, current would flow and lit up the little light bulb. And that's what you would see. This is the concept of a generator. You turn a loop in a magnetic field and it shoves charge. Now, there's also another way to think about this, and you could think about this entire setup in terms of Lenz's law. Here's how you would think about it in terms of Lenz's law if you wanted to. You would say, okay, wait, sorry, let me clear out of this thing. Bye. Excuse me, so sorry. Okay. No, come back. Yay. Okay, here's how you think about it in terms of Lenz's law. You would think about it this way. You would say, okay, there used to be no flux through this little thing here. But then this loop turned. And when it turned out towards you, well, now all of a sudden there is flux going through the loop this way. And that was not the case. So the loop likes it the way that it used to be. And the way that it used to be is that there was no flux. So the loop will attempt to create flux going back the other direction this way. That means that on the pink side here, which is my long edge, you see that in order to undo the change in flux, my fingers point back through the loop, my thumb points up. So the shove on the positive charge will be up on the pink side and down on the regular, not pink side, or up on the long side of my wire as I've drawn it in my picture, and down on the short side of my wire as I've drawn it in the picture. So you could do this whole thing with Lenz's law. Now, let's talk about the next stage in the rotation, because the rotation is not over yet. Here's what happens. This little wire starts this way, and then it makes a turn. Now, when it turns, this little wire is now parallel to the loop. And here's what I want you to see when this little wire is parallel. The wire on the front, the pink wire, or the long-edged wire, is now moving. Actually, I'm going to draw it with my blue once again. The long-edged wire is now going this way. Meanwhile, the short-edged wire is going this way. Notice that there's the bell. Notice that each side of the wire is moving parallel to the magnetic field, which means you have moving charges that are moving parallel to the field. Well, here's the issue with that, is that the magnetic field won't shove on parallel moving charges. It'll only shove on charges when those charges are moving perpendicular to the field. So when you have charges moving parallel to the field, you'll get no shove. And so what happens here is that just for a brief moment, you have no EMF that is created, and you have no current in the little wire right now. Here's what might have been hard to see. When I was using my little generator to light up my little light bulb, the lighting was not consistent. It was not consistently bright. What you would see is that this little light bulb tends to kind of flicker a little bit. It goes brighter and then goes dimmer, and goes brighter and then goes dimmer. That's because there's a point in the rotation of the wire where you actually have no EMF and no current flowing through that little wire. And so at that point, you would see the light bulb as completely dark. But then let's look at the third situation. As this thing continues to turn, now this end of the wire, my pink end of the wire, my long end of the wire has ended up over here. Meanwhile, my shorter end of the wire has ended up over here. And so now it's going to continue to turn, and it's going to continue to turn in that nice perpendicular fashion. So now we see this end of the wire is going into the page. This other end of the wire is coming out of the page like this. Hey, could you use your right-hand rule and figure out which side will become a positive and which side will become a negative? Okay, here's what you should have said. You should have said, I'm going to use my right-hand rule. My fingers point in the direction of the magnetic field. For me, that is to the right. My thumb, I'm going to do I'm going to do this out of the wire first. My thumb is going to point in the direction that the wire is going, which is out of the page. My palm shoves up the positives, so the positives are going to go this way. Meanwhile, on the other side, my fingers point in the direction of the magnetic field. My thumb points into the page because that's the way that the wire is traveling. Now my palm is going to shove positives down this way, which means the positives are going to go around in a circle like this, and this is going to end up being a positive end, and this is going to end up being a negative end right here. If I connected this to a little light bulb, like so, with my... I got my picture in the way sort of here. Then I have a little light bulb right here. Yeah. Okay, perfect. Now, this time, once again, I'm going to get current that is flowing from the high potential side to the low potential side like this. So my current is going to flow this way, and my little light bulb, once again, is going to light up in all kinds of glory and brilliance and wonder. It's going to look amazing. Now, here's what I want you to see. Do you notice that at first, when we look over here, this end of the wire, my short end of the wire, do you see that the short end of the wire was a positive side and the long end of the wire was a negative side? Then over here, now the short end of my wire is a negative and the long end of my wire is a positive. That means that the current actually flipped directions. And the current will change directions like this every half rotation. For this reason, a generator is always going to produce alternating current by default. It'll always produce alternating current by default because every time this loop changes positions, then which side ends up positive and which side ends up negative is going to flip-flop, and so the current is going to switch too. This is why the current that comes from the power plant is alternating current, is because the power plant uses a generator. It doesn't send a giant battery worth of energy to your house. It uses a generator to send energy or to send electricity to your house. And so all generators on their own naturally produce alternating current. Now, there are ways to change that alternating current to make it into direct current, but that is not something that we are going to cover at length in this video. But please let me know if you have questions about it, because it really is like fascinating stuff there. We use a device called a commutator. Anyway, not important now, but that's the main idea. So, generators produce alternating current is the main idea. Now, have you noticed before that all generators are kind of spinny sorts of things? Like, anytime you have a power plant or anything that's trying to create energy, have you noticed that's kind of a spinny thing? Well, that's because we're trying to get a wire to spin in a magnetic field. The way that most power plants run is most power plants run by coal power. So here's what happens is we heat up some coal, and the reason why we burn that coal, there's the bell. The reason why we burn that coal is we burn the coal in order to heat up water. The water boils and it creates steam. That steam travels up towards a little turbine, and the steam turns the turbine. If the steam is turning the turbine, well, that little turbine is connected to a little loop of wire in a magnetic field. So it turns the turbine turns a little loop of wire in a magnetic field, and it creates electricity. And that's the idea of a power plant. But a lot of people say we don't love the idea that we're burning coal in order to make electricity. That's not really great to use all of our fossil fuels that way. So maybe there's something else that we could do. And so they say, what if we used water? And the idea is that they use water, and they use a little waterfall to create electricity. Well, here's the idea behind that is, hey, if you get water to fall, and it falls over a little water wheel, it spins the little water wheel. And if it spins the little water wheel, applying a torque to that little water wheel to make it spin, to increase that rotational speed there, then what you're going to get is you're going to get a little wheel that is now spinning. That little wheel is connected to a little wire loop. That little wire loop is in a magnetic field, and so it's spinning a little wire in a magnetic field. Same thing with windmills. They said, hey, what if we didn't use water? What if we use wind? So they set up a giant windmill. The wind blows. It spins the windmill. Hey, you better bet that that little windmill is connected to a little loop of wire. That little loop of wire is in a magnetic field, spins the little loop of wire in a little magnetic field, and hey, don't you have electricity? So almost all of our types of electricity things are all based off of spinning. And the idea is if you can spin a little wire in a magnetic field, then you can create electricity. That's the whole idea. Hey, let's talk a little bit about Faraday's law here. Let's say that I tasked you. I said, hey, I would love for you to build a generator, but can it please be a super generator? Like, I want serious amounts of electric potential difference between these two ends here. I want a very serious EMF. Can you give me a very serious EMF? Well, you would say, well, yeah, for sure. This whole thing is based on Faraday's law anyway, which is E equals negative N, that's the number of loops, times the change in flux, which is a change in B or A or cosine of theta. In this case, it's definitely a change in cosine of theta, all over a change in time. Hey, can you give a quick thought to this? How are you going to build a generator that maximizes the EMF? What variables could you change? You say, well, Miss Wilson, there are quite a lot of things we could do here. For one thing, we could just add a bunch of loops to the center of the magnetic field. If you add a bunch of loops to the center of the magnetic field, are you for sure creating a bigger EMF? Yep, totally. The other thing that you say that you could do is you say, well, we could create a stronger magnetic field. If we create a stronger magnetic field, that's going to generate a greater EMF, which is absolutely true. And the last thing you say is, actually, there are two more things you say, sorry. The next thing you say is you say, well, what if we made a loop with a greater area? Wouldn't that create a greater EMF? And I say, yep, for sure. And the last thing you say is you say, we should spin that thing faster. And isn't that what we saw with our little generator? The faster you spin it, you decrease the time for the change in flux. So the faster you spin it, the more EMF you produce. And isn't that what we saw with the little light bulb? That the faster you spin it, the greater the potential difference across the ends of the little light bulb and the brighter it burns. So those are the ideas that you could use in order to create a generator that has a even stronger EMF. And that's the idea. That is a little bit on generators. Next, we're going to talk about motors. And for that, I got a whole new tab. Let me go ahead and get it pulled up here. Okay, here we go. Here is a little motor. Now, you're looking at that and you're like, wait a second, Miss Wilson, that's not a motor, that's a generator. I know because I just saw them on the last page. Well, it turns out that motors and generators look exactly the same. Here's the difference. Motors are let's start with generators. Generators are a device that converts mechanical energy into electrical energy. A motor is a device that converts electrical energy into mechanical energy. So this is super common, say, if you wanted to make something spin. Like we saw before, if you take the motor or the little generator and you connect it up to this battery here, the generator that used to create electricity, where you would spin it and it would create a little light bulb that lights up, now, when you connect it to a battery, you get something where the electricity powers the spinning motion. It's the same device, but doing a different thing. One uses motion to create electricity. The other one uses electricity to create motion. You could see how both could be very helpful to us. Like, motors might be helpful to us in the case of, well, if you ever wanted anything to spin or to move, then you might want a little motor to control it. Something like your lawnmower, for example, or like the motor in your car. Those kinds of things, you want motion, and so we use electricity to create that motion. Now, let's see exactly how this little thing would work. Here would be the idea. The idea is, now that I'm thinking about this, I'm like, a motor and a lawnmower, I actually have no idea how that works, or if it is like a traditional motor at all. I really, truly have no clue. So don't quote me on anything that I say in select portions of select videos. Okay, here we go. Now, here we go. Here we have a little generator looking thing, but instead of moving the coil ourselves, we're just going to attach one end. Oh, I'm going to do this in a different color, actually. Isn't that so much more fun? Yes, we all agree. Colors are fun. Yes, okay. We're going to attach this end to a positive end of a battery, and let's attach this end to the negative end of a battery. Now here's what's going to happen. The battery is going to create a little current in this loop of wire here. And the current is going to go from high potential to low potential, or from positive to negative. So we're going to get a little current in this battery that is going up this way, across this way, and down this way. Let's use our right-hand rule and see which way this thing is going to turn. Don't we have a little current-carrying wire in a magnetic field? And we know that magnetic fields make forces on current-carrying wires, and we can figure out which way that force is going to go using our right-hand rule. I'm going to take my fingers and I'm going to point them in the direction of the B field. For me, that is to my right, so I'm going to point to my right. You should right now be pointing to your right. My thumb is then going to point in the direction of the current. The current in this case, I'm going to start with this side of the wire right here. I want to see where this side of the wire will go. So I point my fingers in the direction of the magnetic field. My thumb is going to point up in the direction of the current. And finally, my palm is going to be pressing into the page, which means this, or into the board, or into the screen, which means this side of the wire here is going to be pushed into the screen like that. It's going to be pushed away from me. Meanwhile, on the other side, let's use our right-hand rule and see what's going to happen there. We got our fingers pointing in the direction of the magnetic field. Our fingers pointing in the direction of the magnetic field is from north to south, which is to my right. Then I take my thumb, I point it in the direction of the current. That is down. Go ahead and do it for yourself at your home with your computer. Then, if my thumb is pointing down, my fingers are pointing to the right, then my palm is facing out of the screen. So, my little dot here is going to go out of the screen, showing that this little wire is going to go out of the screen. Here's what this means. It means that on one side, this side right here, wait, let me see what side that is. Okay, this side is coming out at you, while this other side gets pulled back away. So what you're going to see is you're going to see this little loop rotate just like that. Let's try another practice problem. Suppose that I redid this whole thing. We'll go back. Okay, now suppose that we scratch everything here. And suppose that we say that this side is not a south anymore. In fact, this side is now a north. And let's say that this side is no longer a north. In fact, now it is a south. Well, then some things are going to happen. Namely, the direction of the magnetic field is going to switch. The direction of the magnetic field used to go to the right, but now, because we've switched the direction of the magnetic, or the direction of the magnets no longer, now it is going to go to the left like this. If I attached this little end of the wire here to a little positive end, and this little end of the wire here to a little negative end, could you see what would happen? Use your right-hand rule. Well, you say, yeah, sure, Miss Wilson, here's what I would see. I would see that the current would go this way in this wire. That's my direction of my current. My current would go down in this wire. That's the direction of my current. And you would use your right-hand rule. You'd say, for the left side of the wire, the side of the wire closer to the South Pole, I point my fingers in the direction of the magnetic field. My thumb points down, and that thing is going to head out of the page. So you'd say that this side of the wire is going to head out of the page. Then you'd say that other side over here, well, let's see, my current is going up. My magnetic field is going this way. And so, oh gosh, did I do this wrong? No, I did it right. Nope, I did it super wrong. Oh man, that is embarrassing. Okay, back it up, back it up, back it up. Pretend I never said anything about out of the page. Nothing like that. No, try again. Okay, Miss Wilson, stop being so goofy. Do it right. Yes, okay, I get it. Magnetic field is pointing this way. Current is going down. So my palm is pressing into the page. And so this little thing is going to go into the page on this side. Meanwhile, on the other side, the current is going up. The magnetic field is going to the left. So that side of the wire is going to come out of the page towards me like this. And this little wire is going to rotate here in those loops. And that's a little motor. And that, ladies and gentlemen, is pretty much all on motors. Let's go ahead and talk about a transformer. Pulling up a new page here. Here it is. A transformer is a device that looks like this. Have you ever tried to charge your phone before? Odds are you probably have, if you have a phone. If you've ever tried to charge your phone before, you know that there are two parts to your phone charger. One part is a nice long cord. The other part is a little tiny cube, and you need both to work. So the little cube plugs into the wall outlet, and then the little cord plugs into your little phone, and you need both. And you know what happens when you're missing your cube, you can't plug in places, and you're like, oh no, what's going to happen? Well, the reason why you have a little cube anytime you're going to plug into the wall outlet is because your little cube is a transformer. Here's what is inside the little cube. What's inside the little cube is basically this giant iron square shaped thing like this that has loops wrapped around one side, loops of wire wrapped around one side, and loops of wire wrapped around the other side. These loops of wire get connected into the wall outlet, but these loops of wire are connected then to the little cord that goes to your phone. Here's why you need one of those. The wall outlets in America provide 120 volts worth of potential difference. That is a very significant voltage. You put 120 volts worth of potential difference into your little iPhone and you think she's going to be okay? No, your iPhone can't handle such things. And so we need a transformer. What a transformer does is it takes really high voltages and it can make them lower voltages. Or it takes lower voltages and it can make them higher voltages. We use these all the time. Like, for example, the power lines carry really, really high voltage from the power plant to your house. But when it gets to your house, you don't want a voltage that's high because it's crazy, crazy high coming from the power plant. So we use a little transformer. A transformer that makes a voltage from a lower voltage let's go this way. A transformer that makes a voltage go from a higher voltage to a lower voltage is what we call a step-down transformer. And a transformer that makes a voltage go from a lower voltage to a higher voltage is what we call a step-up transformer. Let's see how one of these guys works. Suppose that on this side over here you had a small potential difference that we shall call delta. Actually, I'm going to talk on this side first. This side I think is easier to talk first. Let's say that over on this side you had a really big potential voltage. We'll call it delta V1. This is the voltage that is coming from your wall outlet that is going to try to charge your phone, unless the little cube is there to stop it. And the little cube says, no, I'm going to make that into a much smaller delta V2. That's a small delta V that your phone will be able to handle. Here's how it does it. Well, the power coming from the wall outlet is an alternating current, which means it's going to create a current going different ways in these little loops. Hey, you know all about how to figure out the direction of the magnetic field in a solenoid, don't you? Here's what we would say. Let's say that the current starts out going this way. It goes this way on the front and then back the other way on the back. Well, that would create a magnetic field going through these little coils down this way if you use your right-hand rule. So it creates a magnetic field going like this. But then all of a sudden the direction of the current switches, and now the current is going this way. And if the current is going that way, well then the magnetic field is going up this way through the little loops. And the direction of the magnetic field keeps switching. Hey, if you get a magnetic field that is changing directions, the changing direction magnetic field will create a change in flux. And that change in flux will travel not just right here, but it will travel all the way through this way, then all the way through this way, and all the way through this way, making a magnetic field in the whole little iron core. But that magnetic field in the whole iron core is changing direction. So sometimes it's going this way, and sometimes it's going this way, and sometimes it's going this way, and sometimes it's going this way. And so because the entire magnetic field keeps alternating directions, over in these loops over here, which aren't connected to any electrical source, what you have is a changing magnetic field. And that changing magnetic field will induce a current in these loops, since changing flux creates a current or creates a potential difference, as we know according to Faraday's law. This changing flux will create an EMF according to the expression that the EMF equals negative N times the change in flux over the change in time. So now you're going to create a potential difference in these loops. Here's how a transformer actually changes out the voltage and goes from a higher voltage to a lower voltage. The idea is that the EMF 1, which is equal to your first voltage here, is equal to negative, that negative sign is for Lenz's law, the number of loops times the change in the flux all over the change in time, and this is the number of loops on the first side of the wire. Or this number of loops right here. This number of coils. Meanwhile, for the second EMF is equal to negative the number of coils over here, and 2 times the change in flux here, divided by the change in time. Well, here's what's true. Both of these two are going to experience the same amount of change in flux over change in time, because this guy is actually, like this potential difference over here is actually what's causing the change in flux over the change in time, and then this guy is experiencing the same change in flux over the change in time because they are connected around the same little iron donut here. So what we get is if we create the ratio of delta V1 over delta V2, delta V1 equals negative N1 flux over delta T, and delta V2 is equal to negative N2 times the flux over delta T. Our flux over delta T terms are going to cancel out since they're the same for both. And you're left with an expression that looks like delta V1 over delta V2 is equal to the number of loops for the first coil divided by the number of loops for the second coil. And that expression governs how all transformers work. If you have less loops over here, you'll create a lower potential difference. But if you have more loops over here, you'll create a greater potential difference. Likewise, if you have more loops over here, you create a greater potential difference, and less loops over here creates a lesser potential difference. So what you do is you put more loops on the high potential side and less loops on the low potential side, and then you get the potential that you want based on the number of loops that you put in and the ratio of those loops. Now, here's where some students start to freak out a little bit because they say, wait a second, Miss Wilson, so you're saying I can just change the number of loops and get more voltage? That sounds like loops are magical and like I should start investing in loops right now. Because they say, wait a second, Miss Wilson, you're saying that if I had a very small voltage, I could make that small voltage into a very big voltage just by adding more loops to the other side? Seems like a pretty good deal. They say I should start investing in loops because it looks like I can increase energy just by adding loops. Unfortunately, that is not the case because the law of conservation of energy prohibits that. Let me show you what I mean here. Because of the law of conservation of energy, we say that the power output from the first number of loops has to equal the power output from the second number of loops. And I'm going to erase like some of this work here. So I'll leave my little ratios down here, but I'm going to erase all of this. Goodbye stuff. If you could go, that would be really nice. Increase the amount of space I have on my slide so I can write more stuff. Yeah. And that, ladies and gentlemen, was your erasing song of the day. I do hope that you enjoyed it. But now our erasing time is coming to a close, and so our regularly scheduled programming will continue. Suppose that you had some loops like this. Well, the power output from one side has to equal the power output from the other side because we have the same amount of energy. And power, as you know, up above the world so high, power equals V times I. Yes, it's so true. So my delta V1 times my I1 is equal to my delta V2 times my I2. Well, in this example, you can see that my delta V1 is enormous. And my delta V2 is tiny. So my current will make up for it. In other words, what will happen is I'm not going to have a lot of current from the really high potential place, but I am going to have a lot of current here from the low potential place. Hi, Hamdia. Thank you so much. I am going to have a lot of current from my low potential one right here. And so it trades out the current, it trades out voltage for current is essentially what's going to happen. Thank you.
You
Have a great rest of your day.
Sorry.
Oh, no worries. So, energy does end up being conserved at the end of the day because your voltage gets traded for current, or your current gets traded for voltage, is essentially what happens there. So that's a little bit about a transformer. And that concludes our 3-device lesson for today. We started by talking about generators, then we talked about motors, and lastly we talked about transformers. And that pretty much sums it all up. And I don't think I have anything else to say, so I think I'm just going to leave now pretty much in a really awkward way. Okay, well, bye everyone. Thanks for coming, and I'll see you again next time. Bye, good people.